So in the previous video, we found ds. And now let's go back to our original problem, which if we remember, we want to find the magnetic flux, we want to find the transformer voltage, and we also want to determine the polarity of the transformer EMF at time equals 0 seconds. So the magnetic flux is given as phi equals this surface integral. In this surface integral, we already know that the magnetic flux density B was given in the problem statement. And in the last video, we determined that ds should be this positive z hat r dr d phi. And because we use this ds with a positive z hat, we use the right-hand rule to determine that the transformer EMF is going to go from positive to negative. So positive at the top to negative at the bottom, and that's based on the direction that our fingers are curling. And this is going to be important when we want to determine the polarity at the end. So this means that our magnetic flux integral is going to be this equation at the bottom. And now that we have this magnetic flux, we're going to take this surface integral. We're going to need to integrate from dr to d phi, and in r, we're going to be integrating from 0 to r, and in the phi direction, we're going to be integrating from 0 to phi in order to cover that entire surface. And we're also I'm going to note that we're just going to kind of ignore that little gap there between point 1 and 2 when we take this surface integral, and we're going to pretend that the surface is basically totally closed and doesn't have that little resistor. And this means that our magnetic flux is pi r squared b naught sine omega t. So our magnetic flux, the total amount of magnetic field going through that circular loop of wire, is going to be changing based on sine omega t. Now, this means that we have a magnetic flux that looks like this, and the voltage, the transformer EMF, is going to be related to the magnetic flux by a time derivative. So we have a total amount of magnetic field that's going through the loop, and that's changing in time based on this sine omega t. And we want to now find what the transformer voltage is going to be, and that's going to be based on a derivative of that magnetic flux. So if we take the derivative of that magnetic flux, we can see that really the only part of that magnetic flux that's changing in time is the sine omega t. So our transformer voltage is then going to be equal to this equation, which is changing in time based on cosine omega t. So our magnetic flux is changing with sine omega t, but our transformer voltage is changing in time based on cosine omega t. So if we go back to our loop and look at this picture, we have a magnetic field that is z hat b naught sine omega t. So that sine omega t means that the magnitude or the value of the b naught sine omega t is going to be changing in time. Sometimes it's going to be positive, and sometimes it's going to be negative. And we're going to be looking at the transformer voltage, which we've defined as being positive at point 1 and negative at point 2, and that was based on the ds that we used. So we have a flux that's changing in sine omega t, transformer voltage that's changing in cosine omega t, and this looks like this. So we can see that sometimes the flux is positive, and sometimes the flux is negative, and then likewise the transformer voltage in red, the cosine value, is sometimes that value of cosine is going to be positive, and sometimes that value of cosine is going to be negative. And this change is going to be what makes us look at the polarity of V EMF, because sometimes the current is going to be flowing from 1 to 2, and our polarity is going to be positive, but sometimes the transformer voltage is actually going to be backwards. There's going to be a current flowing from point 2 to point 1, so the opposite of the predefined plus and minus transformer voltage. And so this is what we're going to be looking at in the next video when we look at the polarity at time equals 0.